Today we will do some examples to illustrate the concepts on magnetism and magnetic resonance, which we already discussed. Let us go to example in which we are asked to calculate the diamagnetic susceptibility of a helium. Susceptibility means in this case magnetic susceptibility. Given that the average atomic radius is 0.53 angstroms, is the same as 5.3 nanometers. We know that the Langevin expression for the diamagnetic susceptibility for any system, atoms or molecules, is given by chi equals minus mu naught E square R square into n z by 6m, where mu naught is the permeability of free space which is equal to 4 pi times 10 to the power minus 7, well, we will substitute later, and then n for a mole, for a molar susceptibility, this is just the Avogadro number, Z is the atomic number, E and m are the electronic charge and mass, and R square is the mean square radius, so plugging in all these values we find, so Z is 2 for the helium atom. So plugging in all these values we get the molar susceptibility, diamagnetic susceptibility as minus 1.9937 into 10 to the power minus 8. Next, we are asked to calculate the susceptibility of aluminum at room temperature. No, we have been given the susceptibility at room temperature as 0.82 into 10 to the power minus 8. So we are asked to calculate its magnetization in an applied magnetic field 0.25 Tesla. Again we know the relation between the susceptibility mu naught m by b. So the magnetization is chi times b by mu naught. So substituting the values, it turns out that we have into 10 to the power minus 3. Next we are asked to design a cubic mixed ferrite which has a saturation magnetization of 4.6 into 10 to the power 5 ampere per meter. We are given that the lattice parameter of the basic crystal is 0.839 into 10 to the power minus 9 meters. So, basically we have the basic ferrite is magnetite, in which the iron contributes 4 Bohr magnetons, and we mix it with cobalt, right, in which case the cobaltous ion has a magnetic moment of 3 Bohr magneton. So, we are asked to design a mixed ferrite whose saturation magnetization is given. From the value of saturation magnetization given, we write the magnetization in Bohr magneton. So, this is the given value divided by the value of 1 Bohr magneton. So, that would be now, if we have a unit cell, the net magnetic moment per unit cell is this is what we want, times the volume of the unit cell. The lattice parameter is given, this is a cubic lattice. So, it is just a cube of the lattice parameter. So, this turns out to be so we have to make a material which has a magnetic moment of 29.306 Bohr magnetons, and the unit cell of the ferrite has 8 molecules. Therefore, we have to determine the fraction x of cobalt ferrite so that the remaining 1 minus x times 8 are iron ferrite. So, we have this is 8x here, 8x times 3 Bohr magneton plus 8 into 1 minus x times 4 Bohr magnetons. That should be 29.31. So, x turns out to be 0.33. So, that means that we have to mix 33% of cobalt ferrite with 67% of iron ferrite, the magnetite. So, that is the answer. We next move on to the problem in which we are asked to calculate the saturation magnetization of gadolinium, for which we are given the data that the one Bohr magneton gadolinium has an atomic number which is 64 and an atomic weight which is 157.25. It has a density of 7.86 to 10 to the power 3 kilogram per meter cube. In order to calculate the saturation magnetization, we have to start from the atomic number. So, the electronic configuration gives for gadolinium is 4f7, neglecting the inner shells, the outer electronic configuration 5s2, 5p6, 5d1. So, the 5s2, 5p6 is also a closed shell. So, the 4f7 we know has a spin of 7/2 because there are 7 electrons in the 4f shell, and then there is a 5d1 electron which has a spin of half. So, the total spin is 8/2, which is 4. Gadolinium has a half filled shell, so it has a S ground state. So, the angular momentum is only due to spin, and the spin only G value is just 2. So, the magnetic moment per gadolinium atom is the G value 2 times the spin in Bohr magnetons. So, this is 8 Bohr magnetons, and since Bohr magneton is given, that is for one gadolinium atom, and we have to calculate the number of atoms per meter cube, which is just the density times the Avogadro number divided by the atomic weight. So, this works out to be, substituting the numbers, per meter cube. So, the saturation magnetization is therefore just the number of atoms per meter cube times the magnetic moment per atom, and that works out to next. We are told that a paramagnetic salt has 10 to the power 26 ions per meter cube. That is the concentration of paramagnetic ions. Each ion has a magnetic moment of 0.1 Bohr magnetons. So, we are asked to calculate the magnetization in a field of 1 Tesla at 300 Kelvin. Well, we know that the paramagnetic moment, if it is mu, then the magnetization is n mu square by 3 kBt times the applied magnetic field. So, substituting these values, we readily get the answer as next. We are told that a system of electron spins is placed in a magnetic field of 2 Weber per meter square at the temperature T, and we are told that the number of spins which are oriented parallel to the field is twice the number of spins which have spins anti-parallel to the field. That is the data given. From this information, we are asked to determine the temperature T. So, let us write down the expression for the number of parallel spins, the ratio of the number of parallel spins to the total number of spins, and that is given by, because this is the ground state. So, it will be the total number is proportional to in the same way the number of anti-parallel spins, the ratio with respect to the total number is just given by exponential minus mu b b by k by t by the same. Therefore, the ratio of the number of parallel spins to those of anti-parallel spins is just given by the ratio of these two, and that will be dividing one by the other. Therefore, this is just and we are told that this ratio is just 2. Therefore, taking logarithms, therefore, substituting for everything, we can easily calculate the temperature, and it turns out to be 3.87 K. Next is a problem on the magnetic susceptibility of iron at 900 Celsius is 2.5 into 10 to the power minus 4. We are also given the Curie constant C as 3.25 into 10 to the power minus 2 per K. We are asked to find the Curie temperature, for which the standard symbol is theta. In the expression for the susceptibility, and we are told that the temperature is 900 Celsius, which is 11 73 Kelvin. So, substituting here for chi, c and t, we get theta as 1043 K. So, the Curie temperature of iron is 1043 Kelvin. Next is a problem on nickel, which we are told has an FCC structure, face centered cubic, and its lattice parameter is given to be 3.52 angstroms. The magnetic moment of the nickel atom is 0.6 Bohr magneton. So, we are asked to find the saturation magnetization. For this, we start from the fact that it is a face centered cubic structure. So, it has 4 atoms in the unit cell. We are told that the magnetic moment per unit cell, since there are 4 atoms, it is 4 times the magnetic moment of one nickel atom, which is 0.6 Bohr magnetons. So, the saturation magnetization is just 4 into 0.6 is 2.4 into 9.27 into 10 to the power minus 24 divided by the volume of the unit cell, which is 3.52 into 10 to the power minus 30. So, this will give me 5.1 10 to the power 5 ampere per meter. The next question tells us that the saturation magnetization of cobalt is 14.48 into 10 to the power 5. We are also given the density of cobalt as 89,000 kilograms per meter cube, and the atomic weight is 59. So, we are asked to calculate the spin magnetic moment of a cobalt atom in Bohr magneton. To do this, we start again from the saturation magnetization. Let us assume that this spin moment is mu in Bohr magnetons. The density is 8,900. So, the number of atoms, cobalt atoms per meter cube is given by the atomic weight divided by the density times the Avogadro number. And therefore, mu is from 14.48 into 10 to the power 5 divided by, suppose this is n. Substituting for n, well, into Bohr magnetons. And that will be 1.71. Next is a problem on ferrites, in which we are told 18 atomic percent of iron 2 plus in magnetite is replaced by manganese 2 plus. We are asked to find the percentage change in MS, the saturation magnetization. Now, we know that the Mn2 plus ion has 5 Bohr magnetons, whereas iron 2 plus has only 4. So, the percentage change will be 0.18, which is the percentage of iron replaced by manganese, times 5 plus the remaining 0.82 times 4. This is the new magnetization, minus 4 divided by the original magnetization into 100, of course, which turns out to be 4.5%. We now go on to a problem on magnetic resonance, proton magnetic resonance. In a sample of water which is placed in a magnetic field of 1 Tesla. We have an RF pulse used to observe NMR. This magnetic field associated with this RF pulse has an amplitude of 1 Gauss. We are asked to find the width of the pulse, RF pulse. Needed for this pulse to tilt the proton spins onto the RF field direction. We know that at resonance, the Lambda precessional frequency in a static magnetic field is the frequency with which a rotating frame is used, and in this rotating frame, since it has the angular frequency of the Lambda precessional frequency in the static field, it will stay constant. So, the only field which is there which causes Lambda precession in this rotating frame at resonance the only frequency of precession is the factor gamma h1. So, this is the frequency with which the spins are precessing in this rotating frame around the RF field direction. The RF field is applied in a plane perpendicular to the static magnetic field. So, let us take this as the x direction. So, gamma is the magnetogyric ratio of protons. Which is known. We are also told that this pulse is used to tilt the proton spins, which are originally aligned along the z direction, on to the x direction, which is that of the RF field. Therefore, the angle of tilt of proton spins during pulse is gamma h1, the frequency, angular frequency of precession, times the pulse width. And this we are told, since it goes from the z direction to the x direction, which is that of the RF field. So, this angle is given to be pi by 2. So, substituting the value of gamma and the field amplitude, we get the pulse width as 60 microseconds. Next, we are asked to compare the frequencies and signal intensities of NMR and ESR. The assumption is that they are both used in the same applied magnetic field, static magnetic field. So, in the case of NMR, we know from the magnetogyric ratio of nuclei that for a field, static field of 1 Tesla, the frequency is somewhere in the megahertz region. .5 megahertz, for example, for protons. Whereas, in the case of the electron spin resonance, the same, since the magnetogyric ratio involves the mass in the denominator, and since it is electron, which is 1000 times or 1800 times lighter than the nuclei, order of magnitude 3 orders. Therefore, the corresponding gamma value is larger. Therefore, the same frequency, resonance frequency, which involves the gamma, is going to be, if this is in megahertz, this is going to be in the gigahertz or microwave region. Typically in the X band for a spin only sample. So, that is regarding the frequencies. In order to compare the signal intensities are related to the populations. So, population difference depends on population difference between adjacent Zeeman levels. And this population difference is proportional to exponential minus delta E by kBT, where delta E is the energy level difference. Again the energy level separations of the electron, these energy level differences are 3 orders larger than for nuclei. Therefore, the exponential factors are much larger. So, the signal intensities are much stronger in the case of the electron resonance by the same factor, where this is 3 orders higher. Next question concerns NMR of protons in a hydrated crystal. So, there are water molecules of hydration. So, the H2O molecule has 2 protons, and we are asked to explain how one obtains information on the interproton vector in the water molecule. It is usually called the PP vector, proton-proton vector. In order to answer this, we have to start from the dipolar splitting. Of the proton resonance in water. This is given by, we discussed this already, mu by r cube into 3 cos square theta minus 1, where mu is the proton magnetic moment, which is known, r is the distance between protons, and theta is the angle between the PP vector and the applied magnetic field. So, this means that this dipolar splitting of the proton resonance, which gives a doublet structure like this. So, instead of where there was a single proton resonance peak, we will have a doublet structure like this, somewhat like this. So, this is the separation which we call delta H. So, as one rotates the applied magnetic field, the angle theta changes, and therefore, there will be an angular variation of this dipolar splitting as the applied magnetic field direction changes. In particular, when theta is 0, 3 cos square theta is 3, and therefore, delta H is just 2 mu by r cube, whereas for theta equal to pi by 2, delta H has its minimum value, which is minus mu by r cube. So, this is delta H minimum, and this is delta H maximum. So, the splitting varies between these maximum and minimum values. So, one can determine these two, and from a knowledge of these one can find r and theta from the angular variation. So, we know the separation or the distance between the two protons and the orientation of the interproton vector in the water molecule. So, this is the information that one can get from the splitting, dipolar splitting. Next question concerns the so called chemical shift of the nuclear resonance. So, we are told that the NMR occurs at a frequency 300 hertz higher than the frequency corresponding to a standard sample, which is tetramethylsilane TMS. The operating frequency of NMR is a 300 megahertz spectrometer. Therefore, we are asked to calculate the chemical shift, whose standard symbol is delta. It is defined as the ratio of the shift, which is 300 hertz, to the operating frequency, which is 300 megahertz. So, this is 1 part per million. So, for short it is written as 1 ppm.